will give widely diverging trajectories. Population growth is another example, and of course also the weather. To make this point, Lawrence once gave a lecture with the somewhat curious title, "Does the flap of a butterfly's wing in Brazil stir up a tornado in Texas?" In this lecture he posed the question
whether two particular weather situations differing by as little as the immediate influence of a single butterfly will generally, after sufficient time, evolve into two situations differing by as much as the presence of a tornado.
What Lawrence meant here was that the equations modeling the weather show extreme sensitivity to initial conditions, such as the flapping of the wing of a butterfly. And this is, of course, what makes the weather unpredictable. But let us return to our computer experiments. Why does the calculation give different results on different computers? Well, because different computers use a different precision in the representations of numbers. For example, the computer that I just used has a double precision, whereas a simple calculator like this one, for example, has a single precision calculation. So each computer, even the most highly sophisticated one, rounds off numbers to fit within the word size of its memory units. And because the small differences that result from truncating numbers matter, divergences will sooner or later crop up, even with the most expensive computers. I hope you realize the importance of this phenomenon. It should make everybody become very suspicious about computer calculations, which so many people seem to take for the absolute truth. A second implication is that we should become very suspicious about predictions which are based on the kinds of equations that we have been using here. For example, meteorologists who are trying to predict the weather can never have enough observations to cover the complete Earth. They will have weather stations which are located in particular positions, but we don't have data for the positions in between two weather stations. Now, because these small discrepancies, these small uncertainties matter in the total computation, we will never be able to predict the weather for a long time period. Moreover, even if we had very big accuracy, it is enough that there's a very small disturbance, like the flapping of a butterfly's wing, or a small perturbation somewhere, and our further predictions would be way off. The realization that there are limits to predictability is hard to swallow for scientists who, since Newton, have been growing up with the idea that they would gradually unravel all the laws of the universe and be able to turn them into deterministic laws so that they could predict the future and reconstruct the past. For example, Laplace proclaimed in the 18th century that the whole universe was deterministic and by implication fully predictable.
L'état présent du système de la nature est évidemment une suite de ce qu'il était au moment précédent. Et si nous concevons une intelligence qui, pour un instant donné, embrasse tous les rapports des êtres de cet univers, elle pourra déterminer pour un temps quelconque, pris dans le passé ou dans l'avenir, la position respective, les mouvements et généralement les affections de tous ces êtres.
The phenomenon of chaos shatters this dream of Laplace once and for all, because even if this consciousness would know the deterministic laws, it would still not be capable to predict the future. Poincaré was fully aware of these implications already in 1903, and he understood also what the impact would be for weather prediction. Now, on the other hand, there's also a positive message. Many measurements of natural systems, such as the weather, yield apparent randomness. But these experiments now suggest that there may be underlying deterministic laws. Phenomena which are complex and chaotic could therefore be the result of simple deterministic equations. This gives new hope to understand nature, and the discovery of chaos has therefore triggered a whole stream of very exciting new research trying to look at these complex phenomena and trying to understand their underlying lawful mechanisms. We will later see an example of this for turbulence in fluid flow. At the same time, many scientists have been looking at systems which are thought to be deterministic, ordered, and predictable. A good example of this is the solar system. Based on a new awareness of chaos, it has turned out that these systems also exhibit more complex, chaotic behavior than was previously thought. And we are going to have a discussion with Jacques Lascar about this, who has demonstrated that there is chaos and instability in the solar system. But let me return now to the computer experiments with the same equation as before. The question is, given the same system, will there always be chaos? In other words, will there always be this sensitivity to initial conditions? Now, the answer turns out to be no. For example, I will now put in the value a equal to 1.25, and you could see that the dynamics is evolving so that the quantity x1 is evolving to the same value and x2 is also evolving to the same value, which turns out to be 0.2. Now, when two trajectories always go to the same value, we call this particular value an attractor. When I change the value to 2.5, and I let the dynamics go again, then we'll see that after, let's say, 30 time steps, we see that it is evolving to another value, but both trajectories are both going to the same value. You also see, by the way, that the error is now equal to 0. So in these situations, we don't have any chaos at all. In fact, the trajectories move always nicely to the same value. Now, we can see all this better with so-called cobweb diagrams, which plot the value of x of n onto xn plus 1. Now, this is the bisector at which the values map onto themselves, and this is the parabola which plots our function, which, if you remember, is x plus 1 equals a times xn times 1 minus x of n. For the parameter 1.75, we see a staircase moving to the attractor located on the bisector. The same thing for a equals 2.0. For 2.7, we see the same trajectory, but now there is a spiral movement. When a equals 3.2, we see cyclic behavior. The system moves back and forth between two attractors. When we increase the parameter more and more, we are getting closer to 4.0, and we finally end up in chaos. Notice that the iteration is gradually filling up the whole space, and this phenomenon is called mixing and is another characteristic behavior of chaos. The big lesson here is that the same system may show stable, simple behavior and highly complex, chaotic behavior. All of this depending on a parameter which is usually called lambda. One way to visualize this dependence is through a bifurcation diagram, where the parameter lambda is gradually made to evolve, and then you plot the various attractors that the system is going through. So typically in the beginning there would be only one attractor, and after a while you might have a bifurcation into two attractors. Now let me draw such a bifurcation diagram on the computer using the equation that we have been studying before. As you can see, something very strange is unfolding here. As expected, first there is only one attractor, then we get two,